Hi guys, today I'm going to start talking about transcendental functions. What are transcendental functions? They're the ones that cannot be satisfied or cannot satisfy the format of a polynomial function. So it's not going to be like a n x to the n plus a n minus 1 x to the n minus 1 plus, and you keep going all the way to, for example, plus a1x plus a0. Okay, they're not in this format. They're usually trigonometric functions like sine, cosine, the tangent. It could also be the hyperbolic sine, the hyperbolic cosine, the hyperbolic tangent, cotangent, secant, cosecant, right? What else? They're also the kind of logarithmic functions like log or the natural logarithm, where natural logarithm equals the log with a base e, okay, where e equals the limit of 1 plus 1 divided by n, all this to the power of n as n approaches infinity. This is an irrational number, and it's approximately 2.71828 182 846, but it keeps going, right? It's an irrational number, so it never repeats. The decimal spots in here, the decimal houses, whatever you want to call this, decimal places, never repeat themselves, and they never end. They can, for somebody that doesn't understand what an irrational number is, it's a number that cannot be represented by the division of two integers, okay? So that's an irrational number. You cannot do this by p divided by q, where p and q are integers. You can't represent this stuff. Okay, so these are transcendental functions. This is the graph of e, okay? This comes from the book, of course. So e to the x. So when you have e to the x for x equal to 0, you're going to have 1, right? Because e to the 0 equals 1. And then when you have a positive x in here, it's just going to keep going up. When you have a negative x, it's going to be 1 divided by e to the x. So it approaches 0, but it's always positive. So that's the graph. There's something else too, guys. When you go like, what is the limit of 1 to infinity? At first glance, it seems that it's just 1, right? Because you have 1 times 1 times 1. Well, if that's the case, yes, that's fine. But you see, that's not the case, all right? For example, the limit of 1 plus 1 divided by n to the n as n approaches infinity. As n approaches infinity, 1 divided by n in here is going to approach 0, okay? So you have 1 plus 0, 1 to the n. So this is like 1 to infinity, or approaches, right? You can say that it approaches 1 to infinity. And the value is 2.71 and that stuff that we saw. But let's just say that you make 1 plus 2 divided by n to the n as n approaches infinity. Well, 2 divided by n as n approaches infinity is also going to approach 0. And then I have 1 plus 0 to the n. So this approaches 1 to infinity, but the value is going to be different. Okay? If you put this in a computer, it's going to be able to calculate this for you, the limit in here. And, you know, it can just keep going. 1 plus 473.29 divided by n to the power of n as n approaches infinity. Well, as n approaches infinity, this is going to approach 0, and then you have again 1 to infinity, and the limit's completely different from these two. So the limit of 1 to infinity is unknown. You're going to have to work out the equation, okay, to find out what the real limit is, because it's not just 1 times 1 times 1 times 1. No, it seems that it is, but it isn't. Now, you see, the derivative of e, I don't know if I'm making e this way, okay, e to the x with respect to x is e to the x itself. The proof of this is already in one of my math proofs playlists. It's in my math proofs playlist. So in that playlist, you're going to find a bunch of videos, and there's going to be the proof in there. Okay, the proof that the derivative of e to the x with respect to x is e to the x. This is very important. Okay, I'm not going to show the proof here because then it's just going to be repeating content. Okay, if you want to know the proof of this, pause this video and go to my math proofs playlist, and there's going to be the proof in there, and then you come back. Okay, there's something else too. We're going to work on another transcendental function. You remember that the integral, okay, of x to the n with respect to x, okay, it's going to be equal to x to the n plus 1 divided by n plus 1, right? Well, okay, so let's just say that you have the integral of 1 divided by x dx. What's this going to be? This equals the integral of 1 to the minus, right? X to the minus 1 dx. So let's do this. You get this n here and you add 1. So what are you going to have? Minus 1 plus 1 goes to the 0. And then you get this thing and you put it in the denominator. So divided by 0. Now what you have in here is x to the 0 is 1 divided by 0. This doesn't exist. Okay? So what's happening? How can you find the integral of this? The integral of this doesn't exist. Actually, it does. Okay? The integral of 1 divided by x dx equals the natural logarithm of x. And of course, you have to do the plus c, but forget about this plus c for now. So that's the natural logarithm of x. What's the proof? Well, the proof is also in my math proofs playlist. If you go there, I prove this stuff. Okay? Okay, now let's do some exercises here. The derivative of ln 2x with respect to x. Now, the outer function is the natural logarithm, the inner function is 2x. So you derive or you differentiate the outer function, then you differentiate the inner function, right? So it's going to be 1 divided by 2x times the differentiation of the inner function, which is just 2. You cut this, 1 divided by x. Okay. The derivative of ln of x squared plus 1 with respect to x. It's going to be 1 divided by x squared plus 1 times the derivative of the inner function, which is 2x. So there you go. You can get this thing out of here. There you go. That's it. Now, the derivative of x ln of x with respect to x. Okay. Now we have x in here and you have x in here. So we have two functions. We use the product rule for differentiation. So let's differentiate the first one times the second one plus the first one times the derivative of the first one which is 1 divided by x. So these two cancel. Well, actually, no, they don't cancel. I'm sorry. ln of x plus 1. Okay. And now you have the derivative of ln of x. And the whole thing is going to be cubed. Okay? Dx. Well, you have an outer function here, and you got a mid function here, and an inner function here. The inner function doesn't really matter because the differentiation of the inner function here is just 1, so forget about it. This is going to be 3 ln of x, and this is squared. Okay, it's the ln that's squared, not the x. Times the derivative of the inner function, which is 1 divided by x. All right, so you can say that this is 3 ln squared of x over x. Okay. Here's an interesting one. ln of the square root of x plus 1. Right? Now, here's the thing. What is the square root of x plus 1? It's the same thing as ln of x plus 1 to the 1/2, right? Now, there's a property in logarithms that if it's the log of something to the power of something, you can get this power over here. You can multiply it. So this equals ln of x plus 1 times half, which is just divided by 2. And now you have to differentiate that, right? It wants to differentiate this thing. Differentiate this. Oh, differentiate this. Dx, what a mess. And you want to differentiate this with respect to dx. Okay? So, differentiating here, you can put the half outside because it's a constant. And then times 1 divided by x plus 1. And that'll be it. 1 over 2 x plus 1. Let me see here. Let me see here, guys. I'm thinking of a good one here because there are too many. Yeah. Okay. I'm gonna pick this one. This one seems to be nice. So you have the ln, okay, of the whole thing, right? Is going to be x squared plus 1 squared divided by the square root of 2x squared minus 1. And you want to differentiate this stuff with respect to x, okay? Well, you can differentiate. I'm going to put the d here, right? In logarithms, they have another property. When you have something multiplying, you can separate the logarithm and make it a plus. When you have dividing, you can separate the logarithms and make it a minus. So it's going to be the differentiation of ln of x, okay, plus ln of x squared plus 1 squared minus ln of the square root of 2, well, it's going to be 2x cubed minus 1 to the half, right? It's the differentiation of all these things with respect to x. So the first one is just going to be 1 over x, and the second one, because it's you can put this 2 in here, right? So that's what we're going to do, plus 2 times ln of x squared plus 1 is going to be divided by x squared plus 1 times the derivative of this, which is 2x, okay? And then you have a minus here, and the half, I can put it here. So it's going to be minus half, and times ln of 2x cubed minus 1 is just going to be 1 divided by 2x cubed minus 1 times the derivative of this, which is 6x squared. Okay, so times 6x squared. And you can simplify this here. So this whole thing is going to be equal to 1 over x plus 4x over x squared plus 1 minus, this is going to be 3, right? So you have 3x squared over 2x squared, 2x cubed minus 1. Let me see. Yeah. So I got another one here. Now I have a y equals x minus 2 squared divided by square root of x squared plus 1. Okay? So we already know how to do this, but this is a different way of doing it, because you see, if you want to do this, you're going to make, this is g of x, right? And this was going to be f of x. So it's going to be g of x times the derivative of f of x minus f of x, the derivative of g of x divided by g of x squared. Yes, you can do that. There's another way of doing this. I'm just going to show this to you guys. You can apply ln all over, okay? So you can put, if this is equal to this, that means that ln of y equals the ln of this thing, okay? But I already showed you guys that if it's division, okay, it's going to be a minus. You can separate the logarithms. With this 2 here, you can put it in front. So I'm going to do this stuff already faster, right? So it's going to be the 2 ln of x minus 2, because I'm going to put the ln here, right? ln here and ln here. So that's why I'm doing this. So 2 ln of x minus 2 minus Well, this is x squared plus 1 to the half. It's going to be half ln of x squared plus 1. Okay? Now, here's the thing. I'm going to differentiate everything with respect to x in here. And I'm going to differentiate everything with respect to x in here. Okay? But you don't have an x in here. You have a y. But y is a function of x. So remember that you're going to do the derivative of ln of y with respect to y times dy dx, right? This is what you're going to do. And dy dx is just equal to y prime. So this is going to be 1 over y times y prime. I'm just going to put y prime over y equals, and then just do this in here. It's going to be 2 over x minus 2, okay, minus half times x squared plus 1, right, times 2x, because it's the derivative of the inner function. The derivative of the inner function here is also is 1, okay, so times 1. So you have this thing. Anyway, so what is going to be the differentiation of this? The differentiation, I'm going to drag this over here, put a parenthesis around it. Okay, well, you see what I can do. I'm just going to simplify this even more, further. So you have 2 over x minus 2, and x cannot be 2, okay? X cannot be 2. Minus this 2 is going to be simplified with this 1, so minus 1 divided by x squared plus 1, okay? So now I'm going to delete this. I'm going to put a parenthesis around it. And this y, I'm going to get it out of here and multiply it in here. And there you go. Okay? There you go. So what the heck is this y? Well, it's this. So y complement, which is actually dy dx, that's what you want, okay, equals this thing, because it's this y here, okay, times that stuff. There. And there you go. That's the way it's supposed to be, okay? Now, of course, the book wants to take the minimum common denominator and wants to multiply this term by this term, okay, and then divide and blah, blah, blah. I don't want to do that. I don't want to do that. This is done. This is fine for me. Let me see here. Okay, just seeing some theory here. I might show this to you guys. So let's try another example. Differentiate ln of the cosine of x. Okay, now why am I putting this stuff in here, like this absolute value operator? I'm putting the absolute value operator because you see, what is ln, right? ln is the log with a base e, okay? So let's just say that you have something here. this is going to be equal to something, let's just say x. Now e, what does this notation mean? It means that e elevated to x equals L. Okay, e elevated to x equals L. Well, e is a positive number. So it doesn't matter from as x approaches negative infinity, okay, L is going to approach 0 from the positive side. And as x approaches infinity, L is going to approach infinity too. Okay, so you can see that L is always going to be positive. But the cosine of x sometimes is negative, okay? The cosine from 90 degrees all the way to 270, okay? For guys that don't know what I'm talking about, there you go. Okay, so let's say you got, this is the 0 degree, right? And this is blah, 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 and then you have a 90 degree here. Well, so this is 90 degrees, and here you're going to have 180 over here, and here you have 270, and here 360, which goes back to 0. Well, the cosine is just positive on the right side here. For x from over 90, okay, all the way to less than 270, all this thing here is going to be negative. But the cosine cannot be negative because this is e elevated to whatever in here, which is going to be equal to the cosine. So it has to be positive. That's why I'm putting the absolute value in here. Okay. So differentiate this with respect to x. Well, differentiating this is going to be 1 divided by the cosine of x times the derivative of the cosine of x, which is sine of x. Okay, so this equals the tangent of x. So you can see, you can also do like, okay, so if the ln of the cosine of x equals the tangent of x, what is the integral of the tangent of x? Well, it's going to be the ln of the absolute value of the cosine of x. Okay. It's many formulas, guys. Too many formulas. Oh no, sorry. It's actually going to be the minus tangent. Let me just do one thing here. The derivative of the cosine is the minus sign. So I'm going to put this in here, and here I'm going to put a minus in here. I forgot that. Okay, so plus with a minus, it'll be a minus. So what is the integral of the tangent? Is going to be minus ln cosine of x. Okay. Okay, let's see here. You got a function y equals the ln of x squared plus 2x plus 3, I guess, yeah. And it's asking to find a local extrema or the extrema, which is the minimum point or the maximum point, okay? Like this or this, someplace. In these places, in these points, the first derivative is going to be 0, right? So we derive that it's going to be actually 2x plus 2 divided by this thing, which is x squared plus 2x plus 3. What I did was you differentiate the ln, which brings this to the denominator, and then you have to multiply by the differentiation of the inner function. Okay. Now, when is you want this to be 0? Okay. Now here's the thing: if you want this to be 0, you cross multiply this, right? That means that 2x plus 2 equals 0. Because this is dividing, so it comes over here multiplying. That means that x equals minus 1. all right, and that's the only time that this thing is going to be 0. Now when you put a -1 in here, what are you going to have? You're going to have the ln of, it'll be 1 squared, which is 1, plus, oh yeah, -1 squared, which is 1. And here you're going to have a plus 2 times -1, so that's -2 plus 3. Okay, so it's going to be 4 minus 2, which is 2. So this is going to be the local thing, the local extrema. The point -1 ln of 2. Okay, this is the point in the Cartesian code, Cartesian plane. Now, you can apply, for example, the first derivative, okay, and say, okay, what is to the left of -1? You can put a -2 in here, all right, and see what the derivative is going to be, and then you can put something greater, for example, a 0. You can put a 0 there, okay. So let's try that. Putting a -2 in here is going to be -4 plus 2 minus 2 divided by -2 squared 4 -4 plus 3. So these cancel and you got -2/3. So when you have something like this and you have a -1 here, which is this point, okay, -1 ln of 2. So it's kind of like here, I don't know, kind of this point. Anything that comes to the left is going to have a negative, will have a negative slope. So it comes over here like this. Now what is going to happen here? Is it going to go like this, or is it going to go like that? Okay, so let's put something else. Let's put a 0, something to the right of -1 in here to see what the slope is going to be like. 0 is going to be 2 divided by 3, which is positive, so it'll do this. So we know that this point here is a local minimum. And, well, as a matter of fact, it's a global minimum. Okay, and there you go. -1 ln of 2, that's it. Relative minimum, but as a matter of fact, it's not relative, guys, because there is no other minimum. Okay, there is no other place where the derivative is 0. Okay, the graph is never going to go like this, go up and then this, because here is going to be 0. So you know that it will just keep going up and up and up and whatever. Okay, and over here is also going to keep going up and up. It's never going to do this, because then the derivative is 0 too. Okay, and the only place that the derivative is going to be 0 is this place here. I think that'll be it for now, guys. I think we made a lot of progress for today. Okay.